Alrighty, folks, I hope everybody is doing well. We are going to jump into our next module, if you can believe it, halfway through the semester and into more pointers. So let's go ahead and dive into things here. We've had a little bit of talk about pointers previously, and I've noticed that folks are getting a little bit tripped up. So I wanted to slow us down just a little bit to talk about some different kinds of pointers that'll be able to help us. So this is going to be another introduction, and then of course we'll get a chance to practice throughout the semester. So I just want to give some folks some more tools that you'll see me using that'll hopefully help prevent some errors, and again show you the sort of nice things about the C++ language. So one thing I was wondering about when I first learned pointers is, is it something that's specific to C and C++? And the answer is it's not. There are actually pointers in many different languages. Again, pointers are a powerful abstraction. It's what's going on in your machine, in your hardware. They're using pointers and ways to reference memory and dereference it. If you can sort of go down into the deep levels of it, but many other languages expose this sort of abstraction to you. Even Java to some extent, you can read the wiki page on this just to see. And depending on the language too, they expose different levels or different powers of pointers, which I think is something important to keep in mind. So the Pascal language, for instance, maybe some of you have heard of it, maybe not, has a nice sort of balance of what they allow you to do. For example, you can't just cast pointers to random types, at least in the standard Pascal version. So there's some different things, and maybe something interesting for you to think about as you think about, what languages you like to develop on, or if you go into designing your own language, what kind of things you would take. Or perhaps just thinking about when you're using C++, which features you're going to allow yourself to do in order to make things safe. So just something to keep in mind, and I thought was kind of neat here. So last time we took a little look at the Falling Sands program, so let me just show you a reminder of what that looked like. So I have one example here where I created a little Falling Sands here and I actually added water, and I showed you how to do sort of the sand version here. So you're going to build on top of it for one of your next assignments here. It'll actually be your assignment 7 here. So that was just sort of a nice walkthrough to hopefully help folks get started on that. I'll try to do that a little bit more for the assignments, since one of our goals with this class is just to get comfortable programming in C++. And I think that's how we're going to do it, by just continuing to write some code and get used to the language and debugging and so on. Okay. So just a little bit with that in mind on the course logistics. The fire assignment is going to be due shortly, so hopefully that's been a fun one for folks, again, sort of working with pixels and learning about how things work there. So we'll kind of go from there. And the assignment 6, I've extended the deadline just a little bit, just sort of our cadence here to give a full, I guess I released it a few days ago, but over a week on that, just to kind of help folks get caught up here and make sure, again, you're comfortable with pointers. That'll be a great one to exercise some pointer stuff with. And you're welcome to use some of the stuff that we learned today in your implementation if you'd like. That'd actually be another great exercise. But with that said, let's go ahead and move forward and just talk about pointers a little bit more. So we've seen sort of this illustration before. Again, just recall that pointers are variables that store an address. So we're going to use the equal sign to point to our pointer to some address. So here's a little example I have here where we create a pointer, and of course it points to other floats because we have the star next to it, and we give it some default value here. And then I create a float here, assign it to some values. It's just a regular variable, and my pointer, which I like to prefix with p in front of it, can point to the address of this float here, just some other float type, okay? Just something, so it just points to an address, okay, of that same type. And one thing that I've found helpful in office hours, just sort of explaining to folks, and maybe you'll find this useful, is to, you can do this equivalent line of code here where I have the ampersand, the parentheses, and then some underscore float here. I think that's just sort of a nice way to think of it. This is an operator, the ampersand, but, we can really just think of it as a function here. You can even put the parentheses here. And if you recall, when you've been writing your copy constructors, you've been writing things like operator equals here, and then you put parentheses and then whatever the arguments are. Well, this is the exact same thing. If we wanted to overload operator ampersand, it's just built into the language, or you could overload it for whatever data type that you're creating. This is the same way. It's just your name of your function is ampersand, and it takes some arguments. So you can kind of think of it that way if that's useful, just as a way to keep straight what the ampersand's doing. I've also seen some folks get a little bit tripped up on just passing things by reference here. It looks like I've already got an example here where we're passing things by reference again. And let me actually clean this up a little bit here, because I like to, when you have a data type or a reference, again, think of the ampersand this time on the right side of the type here when you're declaring something. Okay, so it's a little bit of an overloaded symbol, but this is when you're passing by reference. Okay, so just some things to keep in mind there that might be helpful for folks. Okay, so just a little recap there on pointers. Now, some of the problems we can run into with pointers, however, is, at least these three common problems here. And I'll actually add a fourth to the list, the segmentation fault. Although that's not really an explicit problem with pointers, but the main issues are, dereferencing with a null pointer. So that's sort of this first one here, where we've got some pointer here and it points to something that's null, and we're trying to dereference this null value. That's where the name comes from. So this is actually a nice error when you get it, because it's somewhat clear what's going on. Now, obviously, you have to fix it. But the idea here, again, is if I try to dereference this variable, so again, you can think of the star as star and then parentheses if you want to think of it as a function again, and then trying to reassign this value of this variable, that's what's going to cause the null pointer dereference, because you're just trying to set 0 equal to some other value, which the compiler gets confused, because if something's null, it's equal to 0, and we're trying to set 0 equal to 7.0f essentially. That's what the compiler sees that. So it's going to get confused. It knows 0 is a null pointer, or if we've declared it with this null pointer, that's why it's getting upset there. Okay. The second issue that we can have with pointers is what's called a double free, where I allocate some memory here. So this has been one of the good things that we want to do, which is to allocate a integer array with 10 ints, and then we delete it, as I mentioned, because we don't want any memory leaks, and we need to give back the memory that we allocate. That's what we would do with new, and then we use delete with the brackets. But if I try to delete this again, well, it's already been deleted. This memory, this thing that array points to, this chunk of memory is already gone. Okay, so one way to sort of visualize this, and I'll swap the screens here, is in this particular example, remember that array is a pointer. Okay, so we can point into our grid of memory. We've got 10 ints here. So let's create 10 of them here. Here's 8, 9, 10. And when we first create this array here, we're pointing to the first element, and then we offset into this array, to the third thing if we want, and fill in this box or whatever operations we might want to do. So when we delete it, what we're really doing is we're saying, okay, this memory is gone here. Okay, so this pointer doesn't exist here anymore. Okay, so let me get rid of this. So once we've done the delete operation, there was a arrow to this block of memory, but now it's gone. Okay, and now this space here can be used for whatever we want here. But in this case, if we're deleting the array again, well, array is already null. So this is going to give us an error and say, you're deleting something that's already deleted. Or in another case, what might be happening is if you have array 2 here, and let me sort of write it out here. So we delete our array. But if I had a second array, point to our array, and then I try to delete it as well, so I could sort of access, so array is pointing here, I point array 2 also to this array, so it's pointing to the same chunk of memory. So if I delete array here, well, that's going to, again, get rid of this in memory. And then I might also say, well, I should have deleted array 2, right? Or that's what we would think, because it was pointing to the same location. But again, it's going to find that same error where, well, what we're pointing to has already been deleted. It's already null, okay? So that's called the double free. So on occasion, you might have seen that error if you've just deleted things too many times, okay? Now the third type here is what's called the sort of dangling pointer. And this gets exactly to what I was showing. So it kind of combines them or two, but we're referring to something that has already been deleted. So I have this, I'll just call it a shared array here, creating the integers, an array of 10 integers. Then I create some other pointer array that's pointing to the same chunk of memory, delete the shared array, but I'm still referring to something that I think exists, right? I think I'm accessing, or that's what I'm intending to do, this shared array, but it's been deleted somewhere else in my program. Okay, so I cannot dereference there. Okay, so those are some of the issues with pointers, and where we have to be a little bit careful with them. Okay, so again, it's useful to just visualize what's going on with the pointers. So I'm putting on this little picture again, just to again really think about, we have a pointer, it's storing an address of something in a box, whatever this variable is here. Okay, that's just what we're pointing to. And again, the other way I would recommend visualizing pointers is to just take out a a notepad like this or a piece of paper, and just also think about when you create an array, draw a little grid here that this is your memory, and since you're doing new, for instance, array equals new, however many integers you have, let's just say 4 here, and then just draw a box somewhere in the heap here, and go ahead and point to it, because that's what you're creating here. Okay, so just for completeness, that's what you have. That can be, again, just a helpful way to think about what's going on in memory. Okay, so this is your heap. So with that said, though, I want to do a little bit of a review here on just the stack and the heap. And I believe we did a example with this before, but I just want to show you another sort of gotcha point here where we can be careful. So let me go ahead and just do a little bit of a review here of things that can go and be a little bit tricky with folks here. So let's see here. Let me go ahead and I'll just bring in one of our examples here for working with a stack here. Okay, so let's just create a pointer somewhere in star, and I'm just going to say that this is in main here. So some pointer that belongs in main, and we'll initialize it to null pointer. So this is, again, stack allocated. Okay, so it just lives here. Okay, on line 17, and it's going to live within this section here of code, right, within the scope of main. Now, if I create some other function here, foo, and let's just say I create some other array here, let's say 100 things, and let's actually make this a little bit more dangerous. Let's actually just, we'll allocate something else globally. So this is just going to be a chunk of memory allocated in foo. And here is a global piece of data. Or what I'm really just trying to show is just something that's going to live or persist beyond this foo function. So this was something I had showed folks a few other times. So I'm just, I'm indexing it or putting the prefix of this variable with a g underscore to indicate that's a global piece of data. Okay, so it's just going to be accessible everywhere. That just helps me remember a little bit. So let's say if I just point into this function here, and let's say whatever the array is at value, 98 or something, we can do that, but after we call foo here, and then maybe we allocate, something else here on the stack. Let's say we make 900 integers, and then we, let's just print out the value of our pointer here, g pointer here, okay? And let's see what happens here. We're going to make this potentially dangerous, but let's see if we can show the dangers of, again, stack allocated stuff here. So I'm going to compile this with GDB. And let's just to make things a little bit consistent, I want to show people memcopy as well, which is in the string library. It's kind of a weird place for it, but memcopy, just so that we can, or actually memset, just set all the values here to, something like 5. Okay, so let's go ahead and take a look at the arguments of memset, just to see this function here. Set. So this is a handy function, so you don't have to iterate through everything. It'll fill the whole block of memory with the same value here. Whoops, let's do it on CPP reference here, just to show you this example, memset. Okay, so it takes in our destination, what value we're going to set things to, and how many of the values, what the size is. Okay, so how would we do that? Well, we want the destination to be our array. The value we said is just going to be 5, and then, well, whatever the size of an int times 100 is, that's how many bytes we are setting. This is working on 1 character at a time. So however big an integer is, usually 4 bytes, and then 100 of them will make 400 here. Okay, and then we'll just set our pointer equal to, let's just set it to the first element of the array. That'll make it even easier for us. Okay, and then let's do the same experiment here where we're setting this array here to some other value, like 6. Okay, just something different here. And let's go ahead and see if I have carefully crafted this enough, so no mistakes here. And if I run it, well, I'm just getting the address here because it's a pointer, but let's actually dereference it and see what it points to. Okay. So this is the issue here, I guess, that I'm trying to show is, we're setting this thing to, the only way that we're doing the assignment here of our pointer, where it points to, is, well, this first element of the array. But, this data is allocated on this stack. We set it all to 5, so whatever's in this array should be 5. And then we do a memset of 6 of our array here. Just we've done a bunch of stuff, but our pointer, wherever it's pointing, just happens to be 0 here. It's not pointing to anything at all. Now let me see if I get rid of some of these other operations in between our function call. Still 0 in this case, I guess, which is fine. But let's go ahead and just be a little bit more explicit here. And let's try to actually just dereference gpointer and make sure that we point it to, I don't know, the first thing here. I'll just be a little bit more explicit here. Try to run it. And here, in this case, I actually get a segmentation fault here. So let's run it through GDB, see what's going on. So I'll start the program, and I will continue forward. And I'm just going to hit run, so it'll run actually until we get a segmentation fault, which we get at line 31 here from our stack function. But at line 22, it is complaining here. Well, in this case, we just haven't allocated memory here. So let's go ahead and allocate some memory. Let's do it in our main just to make sure that we're being safe here. And we'll say new int, and this can hold 1 integer in it. Okay. So let's fix that up. And let's run our program. Run prog here. So again, this time we allocated memory. And it's not getting any better. We fixed our segmentation fault, so we know we always have a place to store at least 1 integer. But again, we set this value to 5 here. So if I print this out, should I be getting 5 at this point? Why was I getting 8 for, whatever this number is here? Let's try to run it. Oh, because this is I guess, not doing the proper mem set here. And, oh, I've done a little bit of a mistake here. Let me just make these character arrays just to make this a little bit more clear. It's actually not going to work properly with integers here. Just make everything chars. Memset actually only works with byte type, so it's actually putting in 555, whatever that binary is going to be. So that's why we're getting this huge value here. So let's just make everything character just to make things a little bit easier here. Rerun this and then see if we get something printing out here. Okay, so let's go ahead and just revert this back to just pointing at the address. So we're just going to refer to our array here and then just try to access the first element here, which would be the same as dereferencing it. Let's see what happens here. Okay, doesn't like that. This is a pointer to an address. So it's complaining there a little bit. And again, I've got to be a little bit careful with this example because well, we're doing characters now. So let's just set the values to 65, which is going to be some ASCII value here. And then just be very explicit about pointing to the first thing here. And then dereferencing, pointing to the first thing here, etc. Recompile, rerun, and again, so this is the issue here. So we're pointing to something in this array that's been allocated on the stack. And we've created it as A here. And later when we try to access it, we're not getting A back, okay? Because this memory has been deallocated. And again, I'm just going to try to show how it can get worse here. Let's just create our character array and let's see if it'll work here. Sometimes it cooperates. It depends on what system you have. But I'm just going to change a bunch of memory that's nearby here. And we have a bunch of characters, 900 of them. And I'm just going to try to change them to uppercase B's. In this case, it didn't fight too much. But the worst case scenario that can happen is you actually get a B that prints here. If you remember earlier in the semester, I showed an example where that was the case, where the other stack allocated stuff, because it's temporary, gets overwritten by these other values here. And then you just get garbage in places where you think you wrote a valid value. Okay, so anyway, that's one of the dangers. So just a little bit on the stack and heap review there, just a little bit of a contrived example, but I'll go ahead and paste it in for folks. So you'll have this sort of broken or dangerous example here of showing what not to do. So let me put a disclaimer here on what not to do. Okay, so there you go. Okay, so I guess my question then, or thinking about this, depending on how sort of contrived you make the example, or if you've just seen this code, is, can we just build a nice abstraction around pointers? Because, can we do better? Because we saw this example where we were doing some dynamic allocation with our integer arrays. For example, we did this int array class when we were first learning about classes. And, we built this nice abstraction where we had a pointer that we dynamically allocated, and then we could also store its size. And this fit with this sort of resource acquisition is initialization concept, where in our constructors, we do all the initialization, and then our destructor, we automatically delete any of our internal pointers that we have here. This was actually kind of nice. So my question is, can I just do this with a pointer? Can I sort of manage how I'm using it and not have to worry about, am I pointing to things that aren't in scope anymore, and so on? And the answer is, yeah, we could build our own pointer. And this is why this lesson's kind of called Getting Smart here with pointers. So here's an example class for a smart integer pointer, or at least the inklings of a class. We have to learn a little bit more before we fully implement it, but I'll have good news for you in a few moments that we have some stuff built in. But the idea would be you just wrap whatever your pointer is. So if you're working with integer pointers, you wrap that in a class. You have a constructor that makes sure everything's assigned to some value. Maybe it's null or something else. When the destructor is called, you delete. You can handle dereferencing by overloading the arrow operator, and all these sort of ideas. And if you wanted, you could even say, hey, we're not going to allow our pointers to point to other particular data types by overloading the equals operator, or just deleting it and not allowing any copies of your pointers to be made. And that can be a really powerful idea, as we're going to see momentarily here. Okay, so this introduces us to the idea of smart pointers, or it's not really a data type, but it's really just a container for our pointer here. Okay, and C++, modern C++ has these built into it. Okay, so it's really a sort of proxy for us in the sense that we can use it in place of our pointers. So for the remainder of this class, you would never have to use a regular pointer if you didn't want to. Now that we know about smart pointers. So we can construct pointers using one of the following smart pointer types. There's unique pointer, shared pointer, and weak pointer. There's been other kinds throughout the development of C++, but these are the three primary ones. If you actually go to the reference page, you'll see there's something called auto pointer and some of these things, but this has been removed in C++ 17, so we're just going to not worry about it. Okay, so what problems do these smart pointers solve? Well, we won't have to call delete explicitly anymore, so we don't have to worry about what happens when our memory is done with, and we can even avoid calling new as well. We're going to use something like make shared or make unique to do this. And ultimately what we're doing is we're going to be enforcing some constraints with our pointers to make things a little bit more reliable for us, right? We're just wrapping things in a container where we get to define the rules, okay? So what are smart pointers doing? Again, behind the scenes, smart pointers, again, have some different constraints that might be doing some bookkeeping. So things like reference counting, which I'll talk about in a moment. We might be enforcing uniqueness if we can only have one pointer that points to one thing. You could be handling exceptions in the background while the pointer is being created to avoid, if something breaks in the constructor, you can throw an error and sort of handle it. And we'll talk about exceptions. So we still got a little bit more stuff to talk about after this, but let me just go ahead and introduce an example with a unique pointer. Okay, so this is a sort of scoped pointer. So let me bring up this example here for folks that I've got prepared. Unique. And the idea with this is that we have, so here's just some object. You're going to see this in the other examples that I've created just to make things simple. The object here, class, just prints out constructor and destructor when it's being called for our pointers here. Okay, so what's a unique pointer? Well, this is the equivalent or similar to us just creating an object here and then saying my pointer of this type, but instead we are using these smart pointers to create what's called a unique pointer. So a unique pointer avoids us from making copies, okay? So how we create our pointer is we just create it as unique pointer object and then whatever the name is, and then you can allocate. You can use new here, but I'll show you a better way below here. So instead what we just do is we just say std unique pointer, whatever we're going to call it, whatever the type of pointer is, that is the things that it can point to, and then std make unique, and then whatever the type is. So it takes a little bit of getting used to in the sense of, this is a lot to write on one line, or appears to be so, but this is making a unique pointer. And what is this doing? Well, let me go ahead and just run this example here. So I'll make this a little bit bigger here so that folks can see. Grab the compile here, and we want to use at least C++ 17 here for these features, as always. And if I'm running it, you can see, well, each of these cases where I make the pointer here, and then I call it a destructor. Here again, I make the pointer, and then I call it a destructor. So seems reasonable here, but it's destroying this object. It's a pointer to things, so if I want, I can do my object pointer equals and null pointer like this. I can recompile it, rerun it, and we just use it like a pointer. I could dereference it, and reassign it to something. If I had member functions, I could call them. We get the operator equal for free, I guess. But so you use it just like a normal pointer. But again, the idea here with unique pointer is if I try to do something like this, where I create another pointer, my pointer 2, and assign it here to this other pointer, that is, when I'm creating this, it's making a copy, right? Because this is happening during the initialization of this object. If I try to run this, I'm going to get an error. It's going to be a nasty error, but I always try to start from the top. It's going to say in function main. Okay, so I can kind of start tracing from here. Error, use of deleted functions, unique pointer. And it's kind of complaining about this, but if we get to the line here, it's actually just saying, hey, you can't assign this thing that you said was going to be unique here to something that already exists. Okay, so that's the idea. So this pointer can't be assigned to other pointers. And again, what does that prevent us from doing? Well, it prevents us from those sort of double free errors where I've got multiple pointers pointing to the same piece of data. Okay, so that's the idea here. So I'll go ahead and just undo the change here and rebuild it. But that's the real power. Okay, and this can be your sort of default if you want. So I'll just make a note for you there. Okay, so that's the idea. It's just your sort of default. It's your safest. You can't make copies of the pointers, so you don't have to worry about them being passed around. So that's a unique pointer. Now, you might say, well, in some instances, I might want to have a piece of data that I can have multiple pointers pointing to sort of share that information. That could be useful. That's where we have something called shared pointer. So this allows a pointer to have multiple things pointing to it, okay? And as long as other pointers are pointing to that memory, that piece of shared information, it won't be deleted, okay? I'll talk a little bit about how this is working, but I want to go ahead and just show an example of it first. So let me go ahead and open up the shared example, and we have the same object here. So just calling the constructor and destructor, and this time we create our shared pointer here. And it's initialized to whatever its default value is when we create it. That's okay. And this time when I create the second pointer here, my shared pointer 2, it's a little bit different than the make unique because I'm just making shared here. That's what it's doing for creating the object. This creates our second pointer, but now I can, this is allowed that I can have my shared pointer point to this second shared pointer here. Okay, they're the same sort of, the semantics are the same, or the rules are the same, meaning I could basically use these like regular pointers. The difference is in this example from just using a raw pointer and doing this is it's going to keep track of, hey, my shared pointer has, two things pointing to it, to the second pointer. So don't delete this, or rather, this guy can't be deleted if this guy still has is still pointing to it. Okay, and we call this reference counting. So the idea is my shared object pointer 2 has 2 references to it. So let's kind of just compile this, and then we can try to see what's going on here. Okay, so same thing here. We created 2 pointers here, which was kind of interesting. So, I created one here, but I didn't really initialize it, right? I didn't do that until I hit make shared. And then I assigned this pointer to be, okay, whatever the object was we created here. So that's why you're just seeing, one constructor and one destructor being called, okay? So I'm gonna go a little bit out of order from the slides here. I'll revisit them, but I want to go ahead and just walk through this in GDB because it's kind of neat to see what's going on here. And this will be your GDB for the day to learn a little bit of debugging. So let's go ahead and just walk through this one line at a time. So let's go through the start here. So we're in shared, and let's go ahead and just go to the next line here. Here's our shared pointer about to be created. So I'll do print my shared pointer here. Oops, print my shared object pointer. So if I print that, it's empty. There's not too much going on with it here. So let's go to the next line. Okay. And let's go to the next line so that it actually executes, or it did actually execute when we did the make shared there. Then let's print my shared object pointer again here. Oops, a little misspelling, so I have to retype it out. Be my shared object pointer. And then we can see again, this is a shared pointer here. And what's kind of interesting here is it says the use count is 2, week count is 0. Okay, so somewhere it's keeping track of something here. Let's print out my shared object pointer 2. Okay, and this one also, use count 2, week count 0 here. Okay, so what if I just do the next? Let's kind of keep moving through the piece of code. Next here, I'm at my return, so I print my shared object pointer 2. It's not in context. Print my shared object pointer. I think we're both out of context here, so let me actually rerun this. But there is something interesting going on here, this idea of a use count. Okay, so how much is some piece of data that's being internally referred to, how many things are referring to it? Well, for my shared object pointer, we've created one object, so this one points to it. And then because this one also points to my shared object pointer 2, we have 2 references to it, okay? Both of our pointers are using whatever this object is, okay? That's why the use count is 2. Okay, so let me see if I can rerun or walk through this a little bit slower. And we'll see once we leave this scope here at line 38 what the count is. So let me just go ahead and put a break at line 38, and then I'll just rerun the program. And let's see if we can print this out here. Oh, I might need to do it at line 37, sorry. It's not liking that. Break at line 34. Okay, so let's run it from the beginning. And let's print out my shared object pointer. Okay, and it's empty. Print my shared object pointer 2. Okay, so this one here, this pointer, its use count is 1 because we haven't assigned it yet. Okay, so as soon as I move to this next line, both our shared pointer and our shared pointer 2 are going to increment. Okay, so if I go to the next line here, print my shared object pointer, use count is 2 because we're using this object from 2 different pointers. Okay, so that's the idea. And this is doing what's called reference counting, which means there's 2 references to this object. So do not, under any circumstances, delete this piece of memory until this count is 0. Okay, that's the idea. So that's the idea of a shared pointer. So you don't have to worry about deleting the memory, which is cool, right? Once these pointers go out of scope, the reference count for that particular object, that piece of memory, will decrement. And then once the use count is 0, then the memory will be reclaimed. Okay, this is pretty much how garbage collection works in Java, or it's a similar idea where you're tracking how many things point to some piece of memory, and then when you leave scope, you can reclaim that memory. That's when the garbage collection occurs, right? That's why you don't have to have delete in Java, for instance. Okay, so that's a shared pointer. Okay, so one last example of the weak pointer, which is the other way that you can share data, but it's very similar. But it's, as the name implies, it's weaker. So let's go ahead and just run through that example. We'll do it in GDB as well. So let me open up the weak example. So same object that's being created here. And I'll go ahead and compile this example. And let's go ahead and see. So the difference here is we're just creating a weak pointer. We create our object pointer here, so same position, and then I'm going to point my weak pointer to it. Okay, so if I run it, no compilation errors. So let's run it in GDB, the text user interface, and let's go ahead and start from the beginning, move to the next line here. I can print my weak pointer. It's undefined because I have to move to the next line here. So let me print it again. Oops, print my weak pointer. So here it is. Again, it's not pointing to anything, so I'll move to the next line here, where I do the assignment, or rather I've just created my shared pointer and then I'm going to point it. So let me just move to the next line here and print my shared object pointer 2. And this time you'll see the use count is 1 and the weak count is 1 as well, because we're using a weak pointer this time to assign to this data. And basically what this means is we have a weak reference here. Okay, so it's a different count. And what we're saying is we don't really care as much. We want to be able to point to the same data, but we're allowed to destroy this shared pointer or the data that it points to. As long as its use count is 0, even if the weak count is 5, for instance, we can still delete it. Okay, so we're sort of taking this risk here that we could be pointing to some data that's deleted. But the weak pointer has a little bit of a safer abstraction. That's one thing about it. So it can throw us different errors that we can detect. But the other thing is, we might allocate this memory again for this object, and then we'll still hold those weak references to it. We might not be able to do anything with it because they're null, but we'll still sort of point there, which is okay. Okay, so that's the idea with the weak pointer. This is one I use less. My default is, just to sort of summarize as we wrap up here, is to use the unique pointer and be sort of very conservative and say we're going to have one object pointing to something else. If I know multiple things might need to share data, then you use shared pointer. And if you know that you'll need to maybe point to some data, but you don't care if it exists or not, then you can use weak pointer. Okay, so that's sort of the difference between those three, and just some little examples to get us started. You'll see these start to trickle in a little bit more as they're just a little bit safer than raw pointers. Okay, as mentioned, there is something called auto pointer. This is deprecated. We just don't use it, right? Because we're using C++ 17. Okay, so I'm going to kind of power us through. We saw our little example here with GDB. So I'm actually going to wrap us up because we're running at about time for where I want to be here. Just kind of reviewing pointers. You can sort of look into the smart pointer if you still want to see the address. So maybe this is worth doing here. Let me go ahead and just rerun this example quickly. Let me terminate this window, and just in GDB, let's start this one, move a few lines, and then again, if we want, we can just print my shared object 2, my shared object pointer, print my shared object pointer 2. So we can see what its type is. And if you're not sure what the pointer is, I may or may not have shown this, but you can do what is. So always trying to show you guys more tools for debugging, just so you can see the type. And then you can try to dereference these. So if you do my shared object pointer 2 dot, and then I'm just hitting tab to autocomplete, it'll show you a pretty big list of things here. So if I do _m, and I'm going to tab to autocomplete, and then the actual pointer, well, I really don't have any data in here, I guess. but you can actually see, what the value is. So for example, let me do that again. Let's see. And if I want, so let me not dereference this, but let me just print it out here. Then you can actually see the pointer address for this object. If you want to see the internal, just like the way that we were working with the raw arrays, this is sort of your technique. So you can either dereference it and just get the actual array, or just see the address here. So if I try to do this again, you can see sort of where in memory these things live. So just wanted to show you that as a tool. Again, the arrays aren't disappearing. They're just wrapped around in a container form, okay? Just to make things a little bit manageable for us if you want to debug what's going on. But for the most part, you won't need to do this because you can trust that the smart pointers are doing what they need to do, okay? So in summary, we want to use smart pointers in this class. They're totally fine. They add a little bit of overhead because they're doing some bookkeeping, but they're going to make our program safer. Today is just sort of an introduction, so when we get to see them more in practice, and maybe I'll show you a little bit more on just how to build a smart pointer from scratch. We need to learn a few more things before we can do that. But just knowing their existence, usage, that you will see them in some of the code that I provide, and that they're the preferred thing for modern C++ programmers. Okay, so that's it. Make sure to do your in-class activity, and then we will check in the next day. All right, take care, folks.